Hello everyone, my name is Matthew and today I'll be giving a short presentation about my work that I presented for Eusipco 2018, and it's titled Online Parametric NMF for Speech Enhancement. And this work has been jointly done with J.Boldt, L.Shi and M.S.Kavalekalam from the Audio Analysis Lab at Aalborg University, and J.Boldt from GN Advanced Science. So in this work, we are mainly looking into the problem of speech enhancement, which has got a wide range of applications in hearing aids, speech recognition systems, etc. And there exists a wide variety of methods for performing speech enhancement, and they can be broadly categorized into supervised and unsupervised methods based on whether they require training data or not. And these supervised methods for speech enhancement have been shown to be superior than the unsupervised methods, especially in the case of non-stationary noise types. And one very popular class of supervised speech enhancement is the NMF based methods. So these techniques, the NMF techniques, allows us to approximate non-negative data using a set of basis vectors and activation coefficients. So the basic task in NMF is to approximate a non-negative matrix V into W and H such that a certain cost function is minimized. And this cost function is typically dependent on the type of data that's being analyzed, and some of the typically used cost functions in the case of speech or music is the Takora-Saito divergence or the Kullback-Leibler divergence. So in this slide we have a basic example of performing non-negative matrix factorization on a 12-second long piano signal. So on the left side you have the spectrogram of this piano signal. So you can see from the spectrogram that the first 4 seconds we play a particular note, and in the second 4 seconds we play a different note, and both these notes are played together in the third segment here. So here we perform NMF of the spectrogram into two basis vectors and the corresponding activation coefficients. And so you can see that we can see from the right hand side that the basis vector corresponding to the first note is active in the first segment, and the basis vector corresponding to the second note is active in the second segment, and both these basis vectors are active in the third segment as both the notes were played together. So in case of using NMF from a speech enhancement perspective, we would have the noisy spectrogram on the left hand side, and on the right for the basis vectors we would have the basis vectors that we have trained for speech and noise separately, since we are considering supervised enhancement here. So traditionally the basis vectors that have been used for traditional NMF based speech enhancement are not constrained by any parameters other than they have to be non-negative. So in this work we investigate the effect of parametrizing these spectral bases using a physically meaningful model. And one such physically meaningful model would be the source filter model, where the speech component is modeled as a combination of an excitation signal which is produced by the vocal cords, which acts as a source, and it has been later filtered by the vocal tract, which can be modeled by an all-through filter that acts as the filter. And so in this work we show that if we then model the noisy signal in the time domain as a sum of autoregressive processes, the maximization of the likelihood corresponds to performing NMF using Itakura cytodivergence as the optimization criterion. And the spectral basis matrix here would consist of the spectral envelopes corresponding to the different AR coefficients along arranged along its columns, and the activation coefficients can be physically interpreted as the variance of the excitation noise that excites the corresponding AR filter. So moving into the signal model, so we assume that the clean speech S of n is additively degraded by the noise signal W of n to form the noisy signal X of n. And the basic task of any speech enhancement system would be to estimate the clean speech S of n from the noisy signal here. And one way to do so would be by using a Wiener filter which is applied onto the noisy signal. But to apply a Wiener filter, we need to know the statistics of speech and noise a priori. And since we do not have access to either the clean speech or the noisy signal or the noise signal, we need to estimate that directly from the noisy signal. And to make this task easier for us, we here model the noisy signal, a frame of noisy signal in the time domain, as a sum of U autoregressive processes. And here the first US autoregressive process correspond to the speech, and the remaining autoregressive process correspond to the noise. And each of these AR process can be expressed as shown here as a multivariate Gaussian, where this is the mean and this is the covariance matrix. So sigma u square is the excitation variance, and QU here is the gain normalized covariance matrix. And this gain normalized covariance matrix can be asymptotically approximated as a circular matrix, which can be diagonalized using the Fourier transform as shown here. So here F is the DFT matrix defined here, and DU is a diagonal matrix defined as shown here. So it basically contains the values of the spectral envelope corresponding to the youth set of AR coefficients along its diagonal. Yeah. So the likelihood as a function of the spectral basis and the activation coefficients can be then written as shown here. And since we are considering supervised enhancement here, we assume that the spectral basis matrix D is known a priori. So the basic task here is to estimate these activation coefficients given the noisy data X and spectral matrix D. So this is done by maximizing the likelihood. So the log likelihood corresponding to this here can be expanded in this way, and here we have diagonalized the gain normalized covariance matrix as we have explained before. And if we then represent du of k as the kth diagonal element of du, this equation can be written as shown here. And if we now then represent the youth component of the approximated spectrum at the kth frequency index as phi hat u of k, and if we then represent the noisy periodogram at the kth frequency index as phi of k, this equation can be rewritten as shown here. And by rearranging this equation as shown here, we can see that the maximum likelihood estimation of the activation coefficients corresponds to minimizing the Itakura cytodivergence between the noisy periodogram vector and the approximated spectrum given by d sigma. So d is the spectral basis matrix which has the spectral envelopes along its columns, and sigma is a vector containing the u excitation variances. Yeah. So in case we observe multiple frames, this corresponds to performing non-negative matrix factorization of this matrix phi, where the vth column phi v is the pseudogram of the vth frame, as shown here. And here we have regrouped the spectral basis matrix as shown here, where this matrix has the spectral basis matrix corresponding to the speech, and this corresponds to the noise. And similarly, the activation coefficients have also been grouped as shown here. So next we move on to the training stage. So we previously assumed that the spectral basis matrix D was known a priori. So in this slide we explain how it's actually trained. So we first train a speech and noise codebook using a basic vector quantizer, and these speech and noise codebooks contain the spectral envelopes corresponding to the speech and noise, which have been parametrized as AR coefficients. And the spectral basis vector corresponding to a particular entry in the noise codebook is computed using this equation here. So here AU are the AR coefficients which corresponds to an entry in the codebook. So in the figure here we have on the left side the spectral envelopes corresponding to the speech, and on the right side we have the spectral envelopes corresponding to the noise in red. And moving into the enhancement stage, since we are concerned with online processing of signals, we assume that at a particular time we just have a single frame. So here phi represents the noisy pseudogram of a particular frame, and since we are considering supervised enhancement here, our objective is to estimate sigma given phi and d, and this is done by maximizing the likelihood. As we explained before, this corresponds to minimizing the rate of divergence between phi and d sigma. And since there does not exist a closed form solution for solving this, this is solved by iteratively using the multiplicative update algorithm. And once you have estimated the activation coefficients, we can construct a Wiener filter according to this equation to extract the clean speech from the noisy signal. So moving into the experiments, we have evaluated our proposed system in some of the typically encountered background noises, that is the babble, exhibition, and restaurant noise taken from the Aurora database, and the speech has been taken from the grid database. And we have evaluated our proposed system both in matched and unmatched conditions. So the matched conditions refer to the case where we train our system for the same speaker and the same noise type that we test on, whereas in the unmatched conditions the system has been trained on a general set of speakers and noise types, and the noise type and the speaker that we use for testing is not included in this training set. And we will denote our proposed methods as Parametric NMF, and we have then compared it to two other methods. One is the non-parametric NMF, where there is no parametrization involved in the creation of the basis vectors, and the other is unsupervised methods. Unsupervised method which we denote as MMSE-GGP, taken from this reference. And we would like to remark here that typically the NMF based speech enhancement methods try to approximate the magnitude spectrum rather than the power spectrum. So in this evaluation here we have done the experiments for both the cases, and these are the experimental parameters. So the AR orders for the speech and noise is taken to be 14, and we have 64 entries in spectral basis matrix corresponding to speech and 8 entries corresponding to the noise. And these are the results for the matched conditions, and we have evaluated the results using an objective measure called STOI, and this is an indicator of the intelligibility of the signal, and it gives us the value between 0 and 1, and the higher the value is, the better the system performs. So you can see that the NMF based methods perform better than the unsupervised method for speech enhancement for all the noise types. And if we compare the parametric and the non-parametric versions, you can see that the parametric versions give us a better result compared to the non-parametric case for all the noise types as shown here. And if you look at the results for the unmatched conditions, you can see that the results degrade slightly in comparison to the previous slide, but we still see that the proposed methods perform better than the unsupervised method for performing speech enhancement in almost all the cases except for this case here. Yeah, so to conclude, we have here proposed an NMF based speech enhancement where the basis vectors are parameterized using a physically meaningful model. And then we have shown that if we represent the noisy signal in the time domain as a sum of autoregressive processes, the maximization of the likelihood corresponds to performing NMF with the integral cytodivergence as the optimization criterion. And we have also shown the benefit of parameterizing the spectral basis vectors using an objective measure called STOI. Thank you for your attention.